Hi there, and welcome to my talk on consensus time complexity in Oblivious message adversaries. My name is Kyrill Winkler, and this is the joint result with AmiPass, Hugo, Rincon, Ulrich, Schmid, and Stefan Schmid. In this presentation, I will first talk a little bit what the consensus problem is in distributed computing, and then show you the Oblivious message adversary model, which is a very elegant and powerful model for dynamic networks, or more precisely, dynamic message passing systems. After this introduction, I will then show you our main results, which for the first time allow us to establish time complexity lower bounds for consensus in this setting. Consensus problem is a quite fundamental distributed computing problem that has been studied extensively throughout the years. One way of explaining it would be to say, let's consider a group of participants. So for example, the people listening to this talk. And let's say each one of us gets a piece of paper with a number written on it. And our task is now to use an unerasable pen to write a number on the back side of the paper, such that each and every one of us writes the same number on the backside, and the number that we write was written on somebody's front side piece of paper. So this task is actually not so hard because we could just agree to wait until I have read my number on the front side, and then I tell you my number, and we all write that number on the back side. But what say if suddenly my voice starts to fail me and you can't hear me, or maybe only some of you can't hear me, can hear me, and some of you can't hear me, then it will become more challenging. So what I want to say is that in the presence of faults, and in particular in the presence of communication faults, which we will consider in this presentation, this problem becomes difficult and sometimes even unsolvable. Why is it an interesting problem? Well, mainly I would say because it is the fundamental task for replica determinism. So it somehow catches the essence of replica determinism, which is the task where you have multiple replicas. So for example, consider a distributed data center where you have multiple copies of the same servers distributed around the globe, maybe with thousands of kilometers difference between them. And you would like that they all behave in the same way so that if one of the data centers is not reachable anymore, then you have still access to your, for example, cloud data. And in order for these machines to behave in exactly the same way, in a deterministic fashion, you will essentially need them to be able to solve the consensus problem. So the Oblivious message adversary model is a synchronous message passing model, which means that the participants, which we usually call processes, are perfectly synchronized in the sense that everyone knows exactly what time it is all the time. And this assumption allows us to assume lockstep synchronous rounds, where each round, as depicted on the right side here, is, well, first a phase of communication according to a directed graph, and then followed by a phase of instantaneous computation. So we do not really consider computational complexity here. We are now really interested only in what kind of communication complexity do we have. The communication each round is imperfect, subject to faults, and this is depicted by a directed graph. So in this picture here, you see, for example, that there is an edge from P4 to P2, which would mean that P4 attempts to broadcast and P2 is able to receive. Actually, also P3 is able to receive. But contrary to that, P2 is not able to send or to reach anyone with its message because it has no outgoing edges. Important to know that there is also no acknowledgement here, so P2 does not really immediately know who received its messages and who did not. Of course, we somehow need now to restrict these directed graphs that we call communication graphs, because if we allow any graph to be played, then consensus is trivially unsolvable, because then we can just play a graph that has no edges and no distributed computing problem can ever be solved here. And this is now where the Oblivious message adversary model comes in, because here we actually assume a set of allowed graphs, and an adversary can play an arbitrary graph from this set in each round. And Of course, adversary here just means that this is somehow the worst case graph that will be played. So the adversary knows the algorithm, knows what the processes are up to, and tries to basically foil their solving of consensus. Now, the first question that arises here is, of course, when is consensus solvable in this model? And this was actually solved by Colomar, Godin, and Peters in 2015 in an article in Theoretical Computer Science, where they basically showed what kind of property this set of allowed graphs must have in order for consensus to be solvable. What still remained open, however, until now was what about the time complexity of consensus? They did provide an algorithm for consensus in the case it was solvable, but it had a rather bad time complexity. It was highly exponential. And so the question really was, until this point, does it have to be this way, or can we actually find more efficient algorithms? As our first minor result, we rephrased the result by Colomar, Godin, and Peters as an algorithm that you can see on the right side here, which we call the decision procedure. This algorithm takes as an input a set of allowed graphs, and basically it constructs a structure on this set of allowed graphs, and then refines the structure by removing edges from it until it arrives at the result for which we can easily use to determine whether consensus is solvable. So this refined NTD is the result I was talking about. So I will give you a brief example of how this operates on the next slide. But for now, the interesting thing to note is that the time complexity of the decision procedure is actually related to the time complexity of consensus itself. So determining whether consensus is solvable or not, and the time complexity of determining this is actually a lower bound, as it turns out, for the time complexity of consensus, which I think is actually quite interesting in itself. So here I give you now examples for how the decision procedure operates. The allowed graphs are basically the graphs inside of these big white nodes. So in this case, we have three very simple graphs as our set of allowed graphs. And what we do initially is we draw this so-called indistinguishability graph structure, where we link two nodes if some node has the same in-neighborhood in both of them. So for example, here we have the red node. We also add the red node as a label. And we basically see, okay, the red node has the same in-neighborhood in both of these graphs. So we can draw this edge. Similarly here, red and blue actually have the same in-neighborhood in both graphs. So we draw an edge with red and blue. Yeah, we also could draw an edge with red here, but I left this out for simplicity. So what is now the decision procedure that basically does the following? It checks for each edge. So for example, for this red edge, is there a graph in this connected component such that the red edge alone reaches everyone? And the answer to this question is no. So this edge is immediately removed. And now the decision procedure, well, it could continue removing edges, and it would, of course, also remove this edge because now there is no connected component, no graph remaining in the connected component where blue and red or a subset of it reach everyone alone. So this edge would also be removed, but actually it does not even have to be. The decision procedure can terminate early because we have now the consensus solvability condition satisfied, which means that for each connected component, there is a node such that in every communication graph of the connected component, this node reaches everyone, in this case, the green node. So, and now for the second example, here things are not looking so good because if we look, for example, here at the red edge and we would like to remove it, we really cannot do it because there is a graph in the connected component where red reaches everyone, has a path to everyone, is what I mean by reach here. And similarly, this edge cannot be removed because, well, here the blue node reaches everyone. So this edge is somehow also protected by this graph here. And so there can be no removal in this structure. And also there is no single node that reaches everyone in all the graphs of the connected component. And so this would be an example where consensus is in fact impossible. Now, our first result will be to show that there is actually an example where the decision procedure takes an exponential number of rounds. What do I mean by this? Well, in the previous slide, we have seen that we could not have removed, for example, this red-blue edge in example 1 immediately, but we would have needed to wait until we have removed the red edge, or the edge that was labeled by red alone. And so this would mean that here the decision procedure would have needed 2 steps to basically remove all the edges. And that's what I actually mean by time complexity of the decision procedure. And so here now, what we do is we define a graph GI. And by defining this graph, we actually define an entire sequence of graphs, G1, G2, and so on, that has an exponential number of members. And this sequence has a few properties, or the GIs of this sequence have a few properties. So first of all, we have this set Ri, which is a set of nodes that can reach everything. And crucially, the nodes Ri have the same in-neighborhood in Gi minus 2 and in Gi minus 1. And furthermore, we have that for 2 different indices I and j, that the Ri and the Rj are disjoint. And what this results in is basically that the decision procedure, when given this sequence of graphs, in the first step, it can only remove the very last graph of the sequence. In the second step, it can remove the, or maybe not remove the graph, but actually remove the edge to the last graph. And in the next step, the edge to the graph before the last graph, and so on and so on. And it really has to painstakingly remove one edge at a time. Since we have exponentially many graphs in this sequence, this basically means that the decision procedure will take an exponential number of rounds. And as we have seen before in one of our results in theorem 14, we show that the time complexity of the decision procedure is a lower bound for the time complexity of consensus. So this shows that, in fact, the time complexity of consensus really can be exponential in this setting. I did not yet tell you about these nodes B and L. So B is actually a set of logarithmically many nodes that is somehow reserved and will never play the role of Ri or Ri plus 1 or Ri plus 2. But instead, these nodes can be interpreted as, well, bits of a binary number, and they basically tell the nodes of Ri plus 1 that they are in one of 2 graphs. So the node of Ri plus 1, in this case, this would encode 0, and this would be the binary encoding for 1 for Ri plus 2. And this would basically just tell them, okay, you are either in this graph or the next graph, but in no other graph. And this is important because this kind of indistinguishability that we would have without this set B would basically not allow us to make this construction. So using a binary encoding technique here really is crucial for this example to work. Yes, and the nodes Li, they are basically everything that remains. So everything but the other nodes is a member of Li. So the leftover nodes, if you want. For a long time, we actually thought that this was already the end of the story, that the time complexity of the decision procedure completely determined also the time complexity of consensus. And now I will show you that this is actually not the case. So there is actually an example, as depicted here in this sketch on the right, where the decision procedure terminates already after 2 rounds and determines that consensus is solvable. However, consensus time complexity itself is exponential. This looks similar to the sketch on the previous slide. Note, however, that this set UI here is a bit more involved than before. So this is actually a set that somehow depends whether I is an even index or an odd index. And also there is an index J now. Basically, we have layers of these communication graphs that are organized in a very, well, let's call it an intricate way. I do not want to go into detail here, but I can assure you that this is a set of communication graphs where the time complexity is exponential. So why the time complexity of consensus is exponential, I should say. So why is it exponential actually? Well, the point is that we can arrange these graphs to sequences in such a way that the sequences of communication graphs are transitively indistinguishable to each other. And here, well, pairwise indistinguishability of two sequences simply means that there is a process that cannot distinguish the two sequences. So basically, it has heard from the same nodes in every round, and also it has heard from also recursively. So it's basically it has observed exactly the same thing in a perfect store and forward algorithm where everyone just records what they saw and sends the recording of the history to everyone else. And this is the pairwise indistinguishability, and transitive indistinguishability just means there is a chain of pairwise indistinguishability between any two members of this set of communication graph sequences. And this set of communication graph sequences has now a crucial property that essentially kills consensus. Well, that is that the set of the broadcasters of the individual members of this connected component of transitive indistinguishability does not intersect. So what does it mean? A broadcast is basically a process that reaches everyone in a sequence of communication graphs. And it is not too hard to see that actually this is a necessary condition for consensus, that some process managed to broadcast its initial value. If you remember the very beginning of the talk, this corresponds to the value that we all write on the backside. It has to be the value of somebody that has reached all of us. It's not a very difficult proof to show that this is actually necessary for consensus. But here we are going even one step further. We actually show that, or we use a result that was established before that shows that actually not only does each individual sequence need to have a value that was broadcasted, but actually the entire connected component of indistinguishability needs to have a common process that in each individual member of the connected component managed to broadcast. And since this is not satisfied here, it's actually well shown that because the sequence has exponentially many graphs, that consensus time complexity is also exponential. So what does this all mean? It means that the time complexity of the decision procedure is not everything. High time complexity of the decision procedure implies a high time complexity of consensus, but it's not the other way around. So it's not equivalent. And this is actually, I think, the most important conclusion here. So first of all, time complexity of consensus is intricately related to the decision procedure in Oblivious message adversaries. Furthermore, it can really be exponential, which is also, I think, quite interesting to know. But the decision procedure is not the end of the story. There is something else still going on because there are examples of exponential time complexity of consensus where the decision procedure actually only takes a constant number of rounds to determine that consensus is solvable. This concludes my talk. Thank you very much for your attention. Please don't hesitate to write me an email if you have any further questions. If anything comes up, I'd be happy to discuss it. Well, thank you again and goodbye.